Hi class, this is a video on photons, and photons are particles of light, and each particle of light carries some energy with it. This is an interpretation of light that came about in the early 1900s as the result of some experiments that were conducted in kind of the years around the very late 1800s and the very first couple of years of the 20th century, 1900, 1901. And these experiments revealed that in some situations, light does not behave as a wave, which is what all the previous experiments had shown. But some of these newer experiments show that sometimes light behaves like a particle. And this property of light becomes very important when you're considering the way that light and matter interact with each other. So matter is made out of atoms. So it's the way that light and atoms interact with each other, or the way that light and subatomic particles like electrons interact with each other. When you're considering this interaction, you really want to consider the particle-like property of light, and that's when we treat light as photons. And in these cartoons right here, these are showing a particle of light coming in, that's a squiggly line, and it's interacting with this atom, and the atom has a nucleus at the center, and then it's got an electron on the outside of it. And these rings, these represent the various energy levels of the electron on the outside of the atom. And what happens when light and atoms interact with each other is that if the photon of light is going to be absorbed by the atom, then what happens is that the electron in the atom can absorb the energy of that photon of light, and it uses that energy to help it transition from a lower energy state to a high energy state. Once that electron is in that higher energy state, it is going to very quickly transition back down to lower energy states. And every time it transitions back down, it re-emits a photon of light. So that is the way that light and atoms interact with each other, is through the exchange of these particles of light, photons. And that's actually, this is what we're looking at right here in this photograph. This is a photograph of the Ring Nebula. This is an example of a planetary nebula. This is something we'll be studying extensively in chapter 20 when we study the various ways that stars end their lives. And medium mass stars like the sun, this is how they end their lives. They become planetary nebula at the very end. And what happens is the star becomes unstable. It starts to pulsate, and it ends up casting off its outer layers right here. These are the outer layers of the star after it's kind of starting to disintegrate. And what's left is the exposed core of the star. And this is very, very hot. In fact, we have a homework problem in chapter 5 related to this object, the Ring Nebula. This object in the very center, we call it a white dwarf star, even though it's not really a star. It's the core of a dead star. This thing is so hot, it produces enormous amounts of ultraviolet light. That ultraviolet light then travels out from the white dwarf star at the center. And the gas from so this is the outer layers of the star. This gas, which previously was part of the star, this gas can absorb that ultraviolet light. It'll absorb the energy of those ultraviolet photons, and then it can re-emit light at a lower wavelength. So it can actually absorb the ultraviolet light and then re-emit visible light. And by understanding the exact way that particles of light interact with various types of atoms, this is what allows us to determine things like that this planetary nebula, we're looking at oxygen and nitrogen and hydrogen. The only way that we can determine that is through our understanding of the way that particles of light, photons, interact with various types of atoms. And so that's why, even though it seems kind of weird to be studying this in astronomy, because these are some of the smallest objects in the universe, but we use that knowledge to understand some of the larger objects in the universe, like stars and galaxies. So that's why this is an important topic in chapter 5. And to put this a little bit into perspective, we look at the electromagnetic spectrum. In the first part of chapter 5, we studied the relationship between the frequency and wavelength of an electromagnetic wave, and we did some calculations relevant to that. And that was mainly related to microwaves and radio waves, if you'll remember. So as you get to shorter wavelength electromagnetic waves, it becomes very unusual to express them in terms of their frequencies. But down here, we talk about them in terms of frequency and wavelength. The next topic we covered was blackbody radiation, and we worked through some problems using Wien's law, and those were mainly related to infrared light and visible light, and maybe a little ways into the ultraviolet. Now we're going to be studying photons of light, so we're going to treat light as little packets of energy, little particles called photons. And this becomes most relevant for visible light, ultraviolet light, and X-rays and gamma rays. So now we're going to complete the electromagnetic spectrum and really talk about X-rays and gamma rays and ultraviolet light more than we have in the past. And one other thing while we're on the slide is the way that we distinguished radio waves and microwaves and infrared and visible, ultraviolet, X-rays, and gamma rays. We can do that by specifying their wavelength. We also know that we could equivalently specify their oscillation frequency, and that would allow us to distinguish these. These have low oscillation frequency. These all have extremely high oscillation frequency. What we're going to learn right now is that there's a third way to distinguish all these various types of waves, and that's based on their photon energy. So you can either specify wavelength, frequency, or photon energy, and this is what we're going to do right now. So this was the result of some work done by Albert Einstein in 1905. And Albert Einstein came to this realization about photons and this equation. And by the way, this is the work that he got his one Nobel Prize for, although he did two other really incredibly important things in 1905. He did this work on photons and interpreting an experiment called the photoelectric effect. This is also the same year that he discovered his theory of special relativity, and he also developed a theory of what's called Brownian motion, which allows you to estimate the size of individual atoms based on more macroscopic observations. So just three really revolutionary things he did in science in 1 year. This is part of the reason that we consider Albert Einstein to be such a unique genius, is just the amount of work that he did in 1 year was really unprecedented. Anyways, Albert Einstein was interpreting some experiments that had been conducted in the years prior to 1905, and these were starting to reveal some paradoxes about light, that it doesn't behave like a wave. And the way he resolved these experiments, the most important of those is the photoelectric effect experiment, is he proposed that light comes as little packets of energy, little particles, which we now call photons. And the way you can calculate the energy of a photon is you can either take this number called the Planck constant, which is down here, and multiply it times the frequency of that light, or more commonly, because we're not going to really use this one at all, we're going to use this, you can take the Planck constant, you can multiply it times the speed of light, and then you can divide it by the wavelength of that light. And the Planck constant is just another constant of nature, very similar to the speed of light down here. It's something that scientists measure. And so the Planck constant is 4.1 times 10 to the minus 15, and it has units of electron volts multiplied times seconds. So this seems very weird at this point, but this will make sense once we work through some calculations in the next video. But before we go there, I'll just tell you the electron volt, that's a unit of energy. It's a very tiny unit of energy, which is relevant to the energy scales of photons and the energy associated with individual atoms. So in the next video, we'll take this equation and we'll work through some actual problems and some problems that are relevant to astronomy.